Hello everyone, I'm Junghyun An, working with InterDigital. I'll introduce our self-supervised deep network S2F2 for high-fidelity 3D face reconstruction. This is a work done by InterDigital and partly supported by Technicolor. 3D face capture is a fundamental research topic applicable to many practical industry areas such as movie, game, XR, metaverse, and so on. There are many ways of constructing high-fidelity 3D face, for example, manually by the artist, by a massive light stage, via photogrammetry with multiple cameras, and so on. However, these methods are time-consuming and sometimes cumbersome. One efficient way of generating 3D face is to capture it directly from the existing images or videos. Our work focuses on this aspect to facilitate the process. In this direct capture, there are two different approaches, the optimization-based and the learning-based methods. The traditional optimization-based methods reconstruct high-fidelity faces with a strategic sequence of iterations, but the process is slow and sensitive to the initial condition of the 3D face. All the listed optimization-based methods on the left highly rely on the facial landmarks detected from the input images or videos. On the other hand, the learning-based methods are fast and robust to challenging poses as they infer facial parameters through the trained neural network. However, it shows lower reconstruction quality compared to the optimization-based methods. We want to tackle this lower quality issue by exploring how to predict the geometric details. Now let's look at the learning-based methods in more detail. One of the first self-supervised learning-based methods, MOFA, was introduced with autoencoder architecture. It highly relies on 3D morphable models, which could also be called statistical geometry and albedo priors. Further self-supervised methods also rely on 3D morphable models, as it is highly efficient on estimating 3D facial models. However, this statistical prior space could cause a limitation in terms of variety of the reconstructing faces. DECA learns medium details with the displacement map, but the albedo still relies on the morphable model. The method with the rich reflectance reconstructs medium frequency details by applying Cook-Torrance BRDF instead of a mere Lambert-Eaton model. It also applied specular prior to better separate the lighting effect from the facial skin. These state-of-the-art methods are fast and robust, but the geometries are bound by the statistical prior space, which becomes weaker in predicting high-frequency details such as wrinkles and folds as shown in the red square area on the input face. We want to learn how to predict these geometric details through an estimation of a normal map. To resolve this problem, we introduce S2F2 architecture as follows. Our proposed architecture consists of 3 stages: coarse, medium, and fine stages. The coarse stage is designed similarly to the MOFA architecture. We first predict the coarse version of face via the 3D morphable model with the illumination and the camera parameters. In addition to the albedo statistic prior, we also apply the specular statistic prior to better disentangle lighting effects from the surface of the reconstructing facial mesh. We use both vertex-wise differentiable renderer DR and pixel-wise differentiable ray tracer DRT to avoid prior space boundness. The loss function for each DR and DRT consists of photo-loss and regularizer terms. More details are described in the paper. In the medium stage, we further enhance the diffuse and specular maps by predicting the delta of each map. More personalized details on the diffuse and specular map will be estimated through this stage. The 3D geometry, illumination, and camera parameters are further enhanced through the medium stage DRT. Finally, at the fine stage, the fine details are predicted through diffuse and normal maps. Here we use U-Net architecture for both diffuse and normal maps enhancements. The projected image on the texture space is fed as input for both U-Nets. We predict both deltas, which will be applied to the final diffuse and normal maps. Like the medium stage, the geometry, illumination, camera, and the specular parameters are further updated for the final phase reconstruction. Next, we compare our methods against the state-of-the-art methods that only capture medium geometry details. Chen et al. 2019 predicted some geometric details, but the coarse geometric shape, especially the facial identity, looks less correct than ours. Our method captures more geometric details and produces better reconstruction on the wrinkle and folding lines. More qualitative and quantitative comparisons are illustrated in the paper. We also reconstructed 3D face frame by frame from 3 different video inputs. On the left shows the original input. In the middle, the reconstructed 3D face overlaid on the video. And on the right, the geometry overlay is shown. Without any temporal coherence analysis, the results still look plausible. To conclude, achieving high-fidelity reconstruction is important for realistic interaction, especially for the metaverse applications. We show that our contributions significantly improve the reconstruction quality of self-supervised methods. In this work, for the first time, we achieved high-fidelity face reconstruction using only self-supervised learning. Precisely, our method captures detailed geometry and spatially varying reflectance at high computation speed. Our method is also robust against challenging lighting conditions and ready for in-the-wild capture. This is it. Thank you for listening. If you have any question, I'll be happy to answer. If you have any question after the session, please contact junghyun.an@interdigital.com.